Okay, great. Let's start today seminar, and in fact it will be a mini series of 3 lectures by Ilya Dumanski from MIT. The title is Perverse Coherent Sheaves on Symplectic Singularities. Ilya, please.
Okay, thank you very much for the invitation. I'm glad to give this series of lectures. And so let me explain what the plan will be. So today, during the first lecture, there will be no new results at all. I just want to kind of convince you that the notion of perverse coherent sheaves, as already existing, introduced by Bezrukavnikov and others, it is a very reasonable notion, and I kind of want to outline what is known about it in two main examples where this notion is applicable, which are nilpotent cone and the affine Grassmannian. Then I will just overview what is known and or expected about the category of perverse coherent sheaves in these cases. And then lecture 2 will be dedicated to the notion of symplectic singularities and kind of the main step from in passing from the existing G-covariant definition to the new definition, which is applicable to symplectic singularities, which is the notion of Lie algebraics and modules over them. And in lecture 3, we'll discuss this notion of perverse coherent sheaves on symplectic singularities in more details and discuss some examples. Okay, so let me start by saying just literally 2 words about the usual notion of perverse sheaves or perverse, maybe constructible sheaves in this, as opposed to perverse coherent sheaves, so perverse constructible sheaves. And here I will be not precise at all. I will be very precise in the required for me coherent case. And here I just want to kind of remind the flavor of this definition. Constructible. Okay, so again, very non-precise. Let X be some complex variety, and let us fix some good stratification of this variety. Can be Whitney stratification or something like that. And then one can consider the derived category of constructible sheaves, which are locally constant along this stratification. So restriction to every stratum is a locally constant sheaf. More formally, I should consider the category of complexes whose cohomology are constructible. But again, I'm not making any precise statements here. And then there is a notion of perverse sheaves with respect to this stratification. It is a certain abelian subcategory inside this derived category mentioned above. So with some conditions, we impose some conditions about how these sheaves restrict to these stratums in cohomological terms. Okay, so that's a very, very imprecise kind of reminder of what sort of object the usual perverse sheaves are. And now the main idea of perverse coherent sheaves is to replace constructible in the above situation with coherent. So we want some kind of derived category of coherent sheaves on a variety, algebraic variety, and then we want to an analog of this perverse category here in this context. That's what's the idea of perverse coherent sheaves is, but it's not even clear what we should put here in so that this category is reasonable. A naive guess could be the following. Let's just consider again the same stratification, and let us consider the category of derived sheaves, derived category of coherent sheaves in some sense, which are smooth, which means locally free, along this stratification. So this would not work. for the very easy reason, let us consider just the structure sheaf O, which is of course smooth along any reasonable stratification. And let us consider morphism from structure sheaf to itself given by some function such that the divisor of this function intersects the open stratum. Then the cone of this morphism is not going to be smooth along this stratification, of course. So this means that the smooth along the stratification coherent sheaves, they do not form a full triangulated subcategory. For example, morphisms between the structure sheaf and itself, which preserve the trivial stratification, are only constant morphisms, so it's not clear what we should consider here. Okay, so but actually there exists a reasonable definition, a reasonable construction for this category, and let me now define it. So this is definition / theorem. It's originally due to Deligne, then due to Bezrukavnikov, and then also due to Arinkin. So this is the year of this original paper of Bezrukavnikov on this topic. So yeah, the idea is that under certain additional assumptions, if we have certain additional structure, then this notion of reverse coherent sheaves can be defined. So
namely, is it algebraic? Do we work with Zariski topology, or we can assume that X is a complex manifold, or I don't know, complex analytic space, probably better. So
this definition was worked out, as far as I know, only for the case of algebraic varieties and Zariski topology.
Okay.
Yeah, so great comment. So yes, let X be an algebraic variety. And the additional structure which we want to have is the structure of an action of some algebraic group. Yeah, let me write G algebraic group. Yeah, and we want to have an action of an algebraic group G on our variety X with a finite number of orbits, and the dimensions of adjacent orbits should differ by at least 2. So this is an important assumption. And the definition, we say that F, an object of this derived category, is perverse if for any G orbit O, let us consider the generic point of this orbit, and we impose 2 assumptions of the following sort. So we have this morphism, and we consider the derived star pullback in the usual sheaf theoretic pullback. It will map to the derived category of modules over the local ring of this generic point in the schematic sense of this orbit. And we want that the derived star pullback of F lies below these cohomological degrees. That's our first assumption. And then our second assumption is that star pullback to the same generic point, Schrieg pullback to the same generic point lies above the same cohomological degree. So
our ground field is what?
Well, for this definition, it can be arbitrary algebraically closed field, but I will.
Why algebraically closed?
Well, okay. Now for this definition, I think anything would work. Yes, X can be over arbitrary field for this definition, but yeah, I think later when I'll deal with Lie algebraics, I'll need that it is of characteristic 0 and algebraically closed because it behaves behaves different, but yeah, here K I think is any field.
Yeah, and so is there any I don't know, easy example which people who
Yes, I will give an example in a second.
you will, okay,
Yes,
go.
here is a picture.
Yeah, go on.
Yes, so let me now say that we have these two conditions. So for those who are familiar with the more standard notion of perverse constructible sheaves, this is can be thought as a direct analogy, but also under more like assumptions of this sort. For those who are not familiar with these perverse constructible sheaves, just those are certain natural assumptions about how these complexes behave when restricted to orbit. So you can think that very roughly speaking, they are concentrated on these in these cohomological degrees on these orbits, but that is very imprecise. But that's kind of what's going on, and it turns out to be a reasonable notion. Yes, we will consider examples.
So this too many O's, O with a subindex generic point, that's okay.
Yes,
so,
that's
yeah, all right, good.
Yeah, and we take pullbacks into the derived category of modules over the local ring of this generic point of the orbit in the scheme. Yeah, sorry, this always like the local ring.
Also, just a question. The condition that G has only finite number of orbits, that's pretty strict, isn't it?
Yes. This is very restrictive notion. So you asked if it is strict or...
Sorry, yes, I was just asking it like if it was as strict as I was imagining.
Yeah. It is pretty restrictive. Yes. So, well, actually, maybe for
what is our motivating space and group action?
Yeah, that's what I will discuss in a second. But two main examples are the nilpotent cone with the joint action and the affine Grassmannian with the loop group action.
There are finitely many orbits for the action on the affine Grassmannian. Anyway, let's postpone it.
Okay. Yeah. Yes. Yes. So yes, regarding the question if this assumption is actually necessary. So if we just want to claim that such a T structure exists, so that the category of sheaves satisfying this assumption is an abelian category, then I think it is not necessary. But if we want some good behavior of this category, like description, like basically the existence of like IC extension, this Artinian property, and so on, then these are actually the assumptions you very much need, and you cannot assume that it's not satisfied. Yes, for the
what is V? Hold on. In IC or V, O is your orbit?
Yeah, I'm going there.
All right.
Yeah, so for now I'm just here. So that's the definition of what is perverse coherent sheaf. Yes, that was kind of the definition part of this definition / theorem. Now the theorem part is that the full subcategory of sheaves satisfying these assumptions, which will be denoted like that, is the category of perverse coherent sheaves. Let me write that. So yeah, that's a full subcategory of our derived category db coh x of perverse sheaves, perverse coherent sheaves. And this is an abelian Artinian category. So maybe let me say that the most surprising part here is Artinian.
Yes. Yeah, but for constructible version, if the group G has finitely many orbits, is it also the corresponding definition gives you Artinian category?
I think yes, you can prove it basically by induction on the number of orbits.
Okay.
On one orbit this is clear, and then it's kind of filtered by support. So yes, I think that's also the case. Yes. So yes. So the key property here is Artinian. Note that the usual abelian category of coherent sheaves is far from being Artinian. Well, maybe let me give a stupid example here. It's not an equivariant, but anyway, so if you just consider the usual abelian category of coherent sheaves on A1, so modules over the polynomial ring, then it is not Artinian, not every object is of finite length. Yeah, so the same would hold in for the usual abelian category of equivariant sheaves in any reasonable example. But for these perverse coherent sheaves, the Artinian property holds. And we also have the description of simple objects in this abelian category. And so they are of the form IC of OV. So here O is the G orbit, and V is a simple G equivalent vector bundle on O. G equivalent coherent sheaves on an orbit. Coherent sheaf on an orbit is the same as a G equivalent vector bundle on this orbit. Let me also write that equivalently. This is an irreducible representation irrep of Gx, where x is some point on this orbit. Yes, and so what's written here? I see. So we take some G orbit, we consider some simple object there, and then the claim is there is a certain canonical way to extend it to the whole category, to extend it to the closure of this orbit, so that this object will be simple in the abelian category of perverse coherent sheaves. So note that there is no Schrick extension for coherent sheaves. And in general, there is also no star extension because the corresponding sheaf can be quasi-coherent. But there is this intermediate extension. So there is a certain canonical way to define the extension from an orbit to its closure so that all simple objects are of this form. Okay, and finally, a trivial corollary of the above is that simple objects form a basis in the Grothendieck group of this category because of this Artinian condition. And the Grothendieck group of this category is just the same as the equivariant K-theory of X, which is, by definition, the Grothendieck group of coherent G-equivariant sheaves on X. So whenever we have such a condition satisfied, whenever we have this notion of perverse coherent sheaves, we have certain canonical basis in equivariant K-theory. And it is an interesting question what sort of basis this is, which is related to representation theory in many examples. Okay, yes, so now two main examples. So as was noted, this condition is very much restrictive. So it is quite rare situation that you have a group action with a finite number of orbits and dimensions differ at least by 2. So namely, there are two interesting examples arising from representation theory, which I know of. It is the nilpotent cone. So here G is a reductive group. We consider its Lie algebra, and then we consider the cone of nilpotent elements. And there is the adjoint action of the group on this N. And it is well known that there is a finite number of conjugacy classes of nilpotents. So this action has finite number of orbits, and also every orbit possesses a Kirillov constant symplectic form, which means that it is even dimensional. So dimensions of adjacent orbits indeed differ at least by 2. So yeah, orbits are even dimensional because of this symplectic structure on them. And another example is the affine Grassmannian. So here we take this reductive group G and we consider G of Langlands series in formal variable T and mod out by G of Taylor series of T. So you can think of, say, group GLN, and just matrix entries are here the Langlands series and here the Taylor series in this variable. And we mod out, and this is called the affine Grassmannian. And so, yes, as was noted in the chat, I guess, already. So this thing is, it's not a variety, it is an int variety. So int, maybe let me say int projective variety. So it is a union of orbits of this group. So maybe, yeah, maybe let me write it here. So G is a union of lambda check. So let me say that orbits of this action are in correspondence with the dominant co-weights. For G, dominant G co-weights. The corresponding orbit corresponding to a co-weight is called Schubert variety, and the whole affine Grassmannian is a union of these closures of these Schubert varieties, and each of them.
Why they're called Schubert varieties if in the finite dimensional story Schubert varieties are closures of orbits?
Yes, I'm so sorry. You're absolutely right. The orbits themselves are usually called Schubert cells.
Although they are not cells in this case.
You mean that they're not like affine?
They're not isomorphic to affine vector spaces.
That is correct. That is correct. But yeah.
Differently from usual Schubert cells, yeah.
That's right. But if you consider the affine flag variety and the Iwahori orbits on affine flag variety, then I think they will be isomorphic to affine spaces. So yeah, but just in analogy, here we can say that this Grill lambda check is a Schubert cell. Maybe let me not introduce this notion. Let me call the closure is called the Schubert variety. And each Schubert variety is a union of smaller Schubert varieties, and there is only finite number of those. So it is a kind of int variety.
Less or equal, maybe.
That is correct. Thank you very much. So it is an int variety with an int finite number of orbits. So on each finite dimensional piece, there is a finite number of orbits, and we can take the limit. So this notion is well defined for this affine Grassmannian story. Okay. So yes, and the rest of this talk will be dedicated to explaining what is known about these two categories. I kind of want to convince you that in both of these instances, the notion of perverse coherent sheaves is very interesting, and there are interesting theorems about this category, interesting applications of this category, and yeah, so that's what's going to happen. So, okay, our first example was the nilpotent cone. Yes, let me start with a very precise example. Let me, for simplicity, just take PSL2 And then the nilpotent cone is what is usually drawn like this, just the quadratic cone. And there are just two orbits, the zero orbit and the everything else orbit. So two conjugacy class of nilpotents for SL2. And simple objects are the following. So there are those which come as IC extensions of zero orbit. So we consider this zero orbit. And then what we should have simple G equivariant sheaves on this orbit. So they're just irreducible representations of PSL2. And the IC extension in this case is trivial. So we just put a sheaf supported at this point. Yeah, and that's it for V being an irreducible representation. And also there is the open orbit, which is everything else here. But now note that so here we should have simple objects which are representations of the stabilizer of a point here. But note that a stabilizer, so maybe let me take some point X here, and the stabilizer of PSL2 X is a unipotent group, one-dimensional unipotent group. It is an easy computation. So there is only trivial irreducible representation, or just one. And in this particular case, so this may be somewhat misleading, but that's why it is the easiest example. In this particular case, the IC extension does nothing interesting. It is just we extend the structure sheaf from the open orbit to the whole closure. It is going to be just the structure sheaf cohomologically shifted by one, which is 1/2 dimension of this orbit. So yeah, and that, so just one irreducible sheaf supported outside of this close point 0. Okay, so that's an example. Now let me return to the general case. So here G, let me say semi-simple. Well, actually, it can be reductive. Maybe let me say reductive connected. Okay, and so one relatively quick application of this category, which I like, is a proof by Bezrukavnikov of conjectures. So here there is a slight problem that it is maybe not very clear how to precisely state the mathematical statement here. But I hope you will enjoy it even without being very much precisely mathematical. So the conjecture of Lusztig independently and Vaughan, which is now called Lusztig-Vaughan bijection, is the following statement: that there is a canonical bijection between the set of dominant weights for G and the following set of pairs OV, where O is a nilpotent orbit and V is an irreducible representation of the stabilizer of a point at this orbit. So the kind of key word here is canonical. So we just say that there is some bijection between two obviously countable sets. But yeah, it does not depend on any choices. And of course, in research of these people, it appeared like it was expected that these bijections should satisfy some good properties. For example, Vaughan studied supports of irreducible Harishchandra bimodules, and this so in his terminology, these bijections should respect some support of these Harishchandra bimodules conditions, but yeah, in particular, this combinatorial bijection independent of any choices should exist. But it was not proved until the work of Bezrukavnikov, and the sketch of the proof is the following: very nice, very easy using this abelian category. So he claimed that this category of perverse coherent G equivariant sheaves on the nilpotent cone is a highest weight category, or here's the word quasi-hereditary category. Now, its simple objects, as described above, are of this form, so they are naturally labeled by this set. I see extensions of these vector bundles on these orbits. And then he proved that the co-standard objects in this category are of the form derived push forward from the Springer resolution. So maybe let me write here that n tilde is the cotangent bundle to G mod B, and it is canonically the set of pairs B n, where B inside G is a barrel, and n is an nilpotent element in B, so an element in the unipotent radical of B. And there is an evident projection from this to n, which just forgets B, remembers just n. And this is a resolution of singularities called Springer resolution. And given a dominant weight, we can lift the corresponding line bundle from G mod B to the cotangent bundle, and then we can consider the derived push forward of this line bundle. Here is, I believe it should be also homologically shifted, just like in this example. So we see that sheaves should be shifted by 1/2 of dimension of the orbits they live in. So here it's like 1/2 dimension of n. Sorry, it's a technical addition. But anyway, yeah, so he proved that the co-standard objects in this T structure are precisely of this form. So
should we know what are the co-standard objects?
Sorry?
Should we know what does it mean to be a co-standard object?
I will not use anything precise. Yeah, in highest weight categories, there is always canonical bijection between simple objects and the cover, like co-standard covers.
What means highest weight category? Should we know that?
Okay, so you can think of the usual category O or something like that, and then there are Verma modules and projective objects and simple objects, and you can always
so what are the co-standard in this framework?
Yeah, so here I believe that like every simple object should have a canonical cover by a co-standard.
Okay, so that's, I don't know, Zhongzhu is not here, but for me it kind of looks like you should know a bit more of representation theory even to understand what's going on. Yeah.
Okay, well, I apologize, but here I just want to emphasize that using some homological properties of this category, one can show that like these are particularly nice objects in this abelian category, and these are also some nice objects, and there is by some purely categorical argument from some category theory, there is a canonical bijection, meaning that every simple has some canonical cover by some object of this form, and that defines the bijection.
Okay.
Okay. Okay. Yes. Sorry if I don't explain everything here. I just wanted kind of to give examples from maybe different areas of representation theory, how this category appears. Yeah, so let me maybe move to another application, which is about so yeah, here maybe I will not, also won't be very precise. So the idea is that we want to study a category of modules over quantum groups at the root of unity, and there is a certain, maybe I can skip this example, but let me say just a very few words. There is a certain finite dimensional subalgebra inside the quantum group, in this case, called small quantum group. And it is a theorem of Ginzburg and Kumar that the homology ring of this small quantum group is isomorphic to the ring of functions on the nilpotent cone. And so we get a functor from the category of modules over this group to the category of equivariant coherent sheaves on the nilpotent cone. And there was a conjecture of Humphreys. So yeah, sorry, here I also will not explain what a tilting object. Let me just very briefly say, so yeah, sorry for that. I will explain everything in the following examples. Here, let me just say that homology of so-called tilting, indecomposable tilting objects in this category are precisely the direct global sections of irreducible perverse coherent sheaves, and certain conjecture of Humphreys follows from this observation due to Bezrukavnikov also. So most of results about this category for the nilpotent cone is due to Bezrukavnikov and co-authors. So another situation where this appears is representation theory of Lie algebras over fields of positive characteristic, and it is due to Bezrukavnikov and Mirkovich, and certain also conjecture of Lusztig about canonical basis in equivariant K-theory, or sorry, just K-theory of Springer fibers was proved by Bezrukavnikov and Mirkovich using this T structure. Okay, and here let me define everything actually. Another application which actually somehow conceptually explains why this category has so many applications is that this category of perverse coherent sheaves appears in one of Bezrukavnikov equivalences. So this is an instance of local geometric Langlands, and the statement is the following: there is a derived category of G equivariant coherent sheaves on the nilpotent cone, and it has a constructible realization, which is the following. So we take the Langlands dual group G check, we take the affine flag variety. So let me define what it is here. So affine flag variety for G check is as before, G of Laurent series mod Ivachori, and Ivachori is the pre-image. Oops, sorry. So we have G, the projection from G of T to G, which is just T to
where I is not equal to I, yeah, because previously you denoted by I something related to simple object, something like that. No,
it was IC.
Ah, I see. Okay, good.
IC is
yeah. Then you're fine. Yeah, good.
Yes. Yeah. So the evaluation morphism it just takes T to 0, and I check is the pre-image of the Borel subgroup under this evaluation map. And so we take this quotient. This is called the affine flag variety. And one considers the category of the usual perverse constructible sheaves, which I started with today on the flag variety. And then one takes a certain quotient of this category. So it is a, let me say that this quotient is the by the full subcategory generated by simple objects, which are I see sheaves of orbits which are not minimal in the corresponding double coset. So let me say here that we have the Ivachor reaction on the affine flag variety, and orbits now are in bijection with the affine wild group. And by ICW, I mean the IC constructible extension of the from this flag W of the constant sheaf on it. And if we take this quotient, then we take the derived category of the corresponding category, then we get an equivalence. So this is one of the so-called coherent constructible equivalences. It is
so hold on, what is constructible? Because I missed something.
Mm-hmm.
What is constructible?
Oh, constructible is this side, because here by perverse we mean the usual perverse constructible sheaves.
Wow, yeah. So probably should write something like otherwise
Okay.
It's a bit misleading. All right.
I'm sorry. Yes.
So yeah, and how you can prove the equivalence between you construct a bijection at the level of generators or something like that. How
you ask how this is proved?
Yeah.
Well, so this is not so easy. I will not explain this, but so there is a paper by Bezrukavnikov and Arkhipov where they prove constructible realization of the G covariant coherent sheaves on the Springer resolution, and then we kind of need to also take certain quotient here. Well, basically, my point is that is a hard theorem, so there is no quick argument for that.
Okay. All right.
Yeah. So this is a whole. There is a whole business. Again, most due to Bezrukavnikov, about two realizations of fine Hecke algebras, and one of them is coherent, so it is of this sort, and another is of this constructible sort, and he constructs equivalences of triangulated categories between some G and G check realizations of related to affine Hecke categories.
Yeah, but on the left-hand side, you have something finite dimensional, nilpotent cone.
Mm-hmm. Yes.
On the right-hand side, you have something infinite dimensional.
That's right. But here I have coherent sheaves, and they are kind of there are more coherent sheaves than constructible sheaves in a certain sense. So
yeah, okay.
Yeah, that's a typical game that's an instance of local geometric Langlands. So there we also have some this sort of equivalences. That is absolutely right. Here, this is something finite dimensional and coherent sheaves on finite dimensional, and this is infinite dimensional, but we consider constructible sheaves. Also, we pass from G to G check, but at the end, we get an equivalent of category. Okay, and what is the statement about this equivalence? It is that here we have the tautological abelian subcategory. So this is the derived category of this quotient, this abelian category. So we have this abelian subcategory here. And the statement is that the abelian category which corresponds to this one on the coherent side, is precisely the category of perverse coherent sheaves described here. So we get that this abelian subcategory of this derived category corresponds to something which naturally appears on this side, like tautologically appears as this subcategory. Okay, and yeah, now how this works. So why actually something like this should hold? It goes back to a result due to Kazhdan-Lusztig, which considered this thing, which is called the Steinberg variety, and they considered the equivariant K-theory of this Steinberg variety and proved that it is isomorphic to the affine Hecke algebra for G-check. So we have an algebra structure here given by convolution and an isomorphism of algebras. And one can show that under this isomorphism, the equivariant K-theory of the nilpotent cone is naturally isomorphic to the two-sided quotient of the affine Hecke algebra. And the two-sided...
Sorry, how n nilpotent cone is related to this fiber product?
We have natural map from...
pullback or what?
No, just the morphism.
Yes, at the level, yeah, and then what?
And then it is...
you mean just at the level of K-theory, not...
Yes.
Okay.
Yes.
All right. And
So,
C
yes,
star acts by rescaling, yeah?
Absolutely, yes. C star just scales the nilpotent cone. And yeah. Okay, yes, and we have this morphism here. It is surjective on K theories, and namely it identifies the K theory of the nilpotent cone with this two-sided quotient of the affine Hecke algebra by the following thing. So we consider the finite Hecke algebra inside this affine Hecke algebra and tensor it by the sign representation of Hecke algebra from the right and from the left. And this kind of two-sided quotient it has no algebraic structure. I mean, it is not an algebra or something, but it respects the structure of Kazhdan-Lusztig canonical basis. So again, I will not use it, but let me say that there is a certain canonical basis called Kazhdan-Lusztig basis in this affine Hecke algebra, and a part of it survives in this two-sided quotient and defines a canonical basis inside this thing. And so the perverse basis in this group, so as I said in the very beginning, simple objects form a basis in the equivariant K theory. And so in this case, this is a very, very nice basis. It is related to, it coincides just with the Kazhdan-Lusztig canonical basis. So
maybe I ask a question, because I vaguely remember this old Kazhdan-Lusztig story, but geometrically it's all on the constructible side, and you have kind of you had two bases. One, two things. One, classes of simple objects, like I see in your story, and classes of Verma modules. Yeah,
that is precisely these sheaves here in the coherent generalization.
Yes, like every simple is a covering of Verma, and yeah, all right, but kind of they both give you a basis in the K theory. So when you recalculate one in terms of the other one, you get these Kazhdan-Lusztig polynomials, and on the coherent side you have only simple basis of simple objects, yeah?
No, you also have the standard basis. Again, here it is precisely given by these sheaves. So
there are analogs of Kazhdan-Lusztig polynomials in that story, or
they're just the same. So this is just two realizations of the same algebra. In this case, so
perverse coherent sheaves somehow correspond to constructible perverse sheaves.
Yes.
This is why perverse basis coherent goes to Kazhdan-Lusztig, and there are also co-standard objects, and they, under this equivalence, go to Verma.
Exactly. Yes.
Yeah. Okay.
Yes.
All right.
Yes. Right. Okay. So that is all I wanted to say about the story for the nilpotent cone. Let me move to the affine Grassmannian side. So explained what is the affine Grassmannian, and here we also have an additional C star action, which just scales the loop. So maybe let me write this C star. If I take some C, then it maps T to CT, so it just scales the T variable, and we can consider graded or ungraded versions of this category. This category is called coherent Satake category. So here again, one application which I will not comment, but I think it is one need to mention it that this category has a meaning in mathematical physics. So, namely, it is believed to be the precisely mathematical definition of half BPS line defects in 4D n equals 2 pure gauge theory. This is due to Couch and Williams, and kind of where this comes from is that this algebra, if we take the covariant K theory of the affine Grassmannian, there is also a convolution. So this is an algebra, and the spectrum of this algebra is the Coulomb branch of this 4D n equals 2 pure gauge theory. So this was defined by BFN, Braverman, Finkelberg, and Nakajima. And this is some categorification of Coulomb branch, meaning that the Grothendieck group of this category is this ring of functions on Coulomb branch, and so this is believed to be the category of line defects in this theory. Okay, now let's move to more like mathematical properties of this category. So it turns out that this category is a monoidal category with renormalized R matrix. So what I mean by renormalized R matrix, so we don't, it is not a symmetric monoidal, so tensor product of AB, or well, here I think I denote this monoidal structure by star. AB is not isomorphic to B times A, but there always is some morphism to this, which may not be an isomorphism. So you should think of categories of finite dimensional modules over a affine loop group or over Yangian, which also possess a similar structure. So let me define the monoidal structure here. So we can consider the following variety, or invariety also, called the convolution diagram. So we take G of loop, the loop group over the current group times the affine Grassmannian, and there is an H holomorphism to the affine Grassmannian from it, which maps a pair Gx to G applied to X in class of it. And then if you have two sheaves inside this derived category on the affine Grassmannian, then there is a certain canonical way to build a sheaf. Oops, sorry. So here it should be gr times gr. So this variety here, and then their convolution is defined as the derived push forward of this thing. so along this morphism, and it is the very same way how one defines the convolution of the usual constructible perverse sheaves on the affine Grassmannian, or convolution, as I said, this thing is an algebra by the very same reasons, and parallel Moore homology of affine Grassmannian is an algebra of by the same reasons. So this is the usual convolution, and this the perversity is preserved by this thing. So convolution of two perverse coherent sheaves is perverse coherent. So this is indeed the monoidal abelian category, and the R matrix maps, they come from some Beilinson-Drinfeld deformation of the affine Grassmannian. So I will not.
What does it mean? You mean the global version of the curve?
Yes. You can take a curve. Say A1 would work for these purposes. Yes, and then you can construct the Beilinson-Drinfeld deformation. I don't know.
I mean that you said that one can think about finite dimensional representations of UQG hat, and there I remember years ago I defined the notion of meromorphic tensor category where R matrices are meromorphic, so it's not an isomorphism but outside of some whatever collection of singularities they are. And so UQ of G hat was an example. So that's what I mean. Is it the same type of structure?
Yes. This is sort of meromorphic, but kind of here I don't. So there you have a one parametric family of automorphisms, and as you say, outside of poles, this thing was an isomorphism.
So this renormalized, just people did not read my paper. Okay, good. So it's meromorphic tensor category. Good.
Yes, something like that.
Perfect.
Okay, so and here I am finishing. So Couches and Williams also proved for G equals GLM that this thing is a quantum cluster monoidal categorification. So let me say a very few words about what it means. So there is a notion of cluster algebra, which is a certain algebra with fixed generators, and the relation between these generators are of the form like x times x prime is equal to sum of two monomials. So let me very informally say something like this. But you can categorify this. So there are three terms in it, and you may require that this relation comes from a short exact sequence in some category. So if your algebra is a Grothendieck ring of some category, then you may want that all these relations come from short exact sequences. And that's precisely the notion of monoidal cluster categorification. So there's a categorical version of cluster algebra. I will not be precise here, but this is a very strong structure on this category, meaning that the Grothendieck group of this category is isomorphic to a certain cluster algebra, and all relations of this sort in this cluster algebra, they come from short exact sequences in this category. So these are classes of some objects in the category, and this relation comes from short exact sequences.
Sorry, there is also notion of quantum cluster. I mean, there is a notion of quantization of cluster algebra. What appears here?
So here, this loop corresponds to this word quantum. So if you remove the loop, then you remove the word quantum.
All right. Okay.
Right. And so let me finish by the same question as we answered for the nilpotent cone before, about what is the perverse basis in this case. So the answer is not known in arbitrary type. There is a very recent conjecture of Fan Chin of what he calls the common triangular basis in cluster algebras, and this is a version of Kazhdan-Lusztig basis for cluster algebras. And we conjecture that this perverse coherent basis in this coherent K-theory coincides with this Chin's common triangular basis. But this is very far from being proved. What is proved is that for G equals JLN again, there is some exceptional isomorphism, which was known to Finkelberg for a long time, that this equivariant K-theory of affine Grassmannian is isomorphic to a certain quantum unipotent cell for affine SL2. So you
what means quantum unipotent cell?
So just unipotent cell is just some like Richardson variety sort variety, meaning that in the unipotent group inside to this affine SL2 to any W, you can assign.
Yeah, okay.
Yes,
all right.
And there is a natural quantization of this thing called quantum unipotent cell. So again, maybe let me remove this thing here and remove quantum word here. So just the unipotent cell for affine SL2 corresponding to this. So note that the fact that we take affine SL2 kind of does not depend on N, on which group we take here, but the affine while group element depends on N. Yes, and then we have this isomorphism of algebras, and then Lusztig defined canonical basis for quantum groups, and in particular, there is a notion of dual canonical basis in this quantum unipotent cell, and it is a theorem of Finkelberg and Fujita, very recent, that perverse coherent basis in this thing coincides with the Lusztig's dual canonical basis in this algebra.
O of Q is a quantized algebra of functions, or what?
Yes.
Okay. Yeah.
Yes.
I can understand.
So again, this perverse coherent basis gives some like very, very nice basis in this algebra, which was studied before. And in general, we expect this, but this is I don't want to comment on that, but there should be some type-independent description of this basis. Okay, so that's where I want to finish today. I'm sorry that that was very, very sketchy in most of details. I wanted to kind of convince you that this notion of perverse coherent sheaves it is not as well known as the corresponding constructible notions due to Billingson-Bernstein and Deligne, and it is much more restrictive, meaning that there are much less examples where one can study it, but in the examples where it is well defined, it has many nice properties and expectations about this category. Yeah,
all
and
right.
in the remaining, sorry, I'm finishing. In the remaining lectures, I will try to present generalization of this notion to a more general setup.
Which has symplectic singularities. Yeah.
That's right.
Okay. All right. Thank you very much. Questions? Well, if there are no questions, so there will be next lecture, second lecture on Wednesday, same time. So Ilya, can you send me corrected kind of your notes, because you wrote something
of
during
course.
your talk. All right, thank you very much, and this is it for today.